run-of-the-mill spyware. Anytime you see malware, it'll do some kind of OS fingerprinting, but particularly on like iOS implants, you'll see it's asking for the iOS version, asking for carrier info, and it's trying to gather device status. So it'll try to figure out what Wi-Fi you're on, if you're connected to Wi-Fi, if the phone is connected to airplane mode. And then it did, things that are probably spying, like recording audio, taking pictures, tracking location of the user. This particular sample also did some things that were unique to this particular threat actor. So they were exfiltrating and deleting keychain items on the device, exfiltrating and deleting other files on disk, and we didn't see any persistence mechanism, but that's also very normal because of iOS system protections. So it is almost impossible to get true persistence in the true definition of it on iOS today, and that's partially because of the way that the boot chain is created. So the iOS boot chain is a series of steps where each preceding binary is going to verify cryptographically the next stage of the bootloader. So what you'll see is the boot ROM will load the LLB and then iBoot, and then that will load the kernel, and that will load the iOS operating system, but it's all leveraging the secure enclave, which is a coprocessor on the iOS chipset that is using a hardware key to cryptographically verify each element. So that's what makes the iOS boot chain so secure. So there are some examples of persistence that Bill's going to talk about that are kind of persistence, but they're not true persistence.
Lowercase p persistence, if you like. Right, so you can divide these into kind of two columns, the ones that are sort of more theoretical and the ones that have been observed in the wild. So in the theoretical column, we have techniques like the one that ZegOps posted on a while back, where, okay, well, you don't actually shut down the phone, you fool the user into thinking that the phone is being shut down, right? Because malware's on the device, it can control anything, it can, when you push the shutdown button, you can hook that and throw up a fake shutdown screen, turn off the screen, make you think it's off, but it's not actually off. So the way the spyware survives a restart is the phone's never actually restarted. So what we've seen in the wild has been actually pretty interesting. Way back in 2016, with the first Pegasus sample we analyzed, there was a pretty clever persistence technique, right? So remember, secure boot chain, everything, certificate verified, yada, yada, yada. Well, okay, what if you replace one Apple sign binary with another Apple sign binary? They're both valid. The signature is totally fine. So it should pass signature verification and all that. So what the threat actors did, Pegasus in that case, was they found this binary RT-buddy-D, which I guess didn't do anything too important because they collaborated it and replaced it with the JavaScript core binary, which, as its first argument, can take the path to a file on disk containing JavaScript, which will then be executed by JavaScript core. So they found that RT-buddy-D was invoked with a early boot argument. So they just dropped a file on disk called early boot and put the JavaScript exploit in there. And then magically on reboot, there was reinfection. So that was pretty clever. Since then, we've seen a little bit more off-the-wall techniques. Like in Predator, the Cytox's Predator spyware in 2021, we saw them using an iOS shortcut automation. So if you have an iPhone and you're like a really hardcore power user, like maybe you've got some complicated home setup where you want when I get home I want the lights to turn on in the entryway or something like this. I don't know, like all these automations that you can think of. So you can also do these for your phone. Like you can say, well, when I open a certain app, lock the phone screen or something, right? Like a sort of a way to maybe get some additional security. But it turns out that you can also use these for persistence, right? You can, in this case, we saw the threat actor have a precondition, which was when any one of 40 some apps is opened, which would happen when the phone is rebooted, then a chain of actions is executed, which results in the phone fetching, not visible to the user, but fetching a web page and rendering it in the background with WebKit. So you just code a URL to your exploit for persistence, and just a normal WebKit exploit, and it loads and reinfects the phone. Small p persists the infection whenever the phone reboots. But I think the larger point here, right, is we don't see like a ton of these cases of persistence just because you don't really need it. You can get persistence through reinfection if you have a zero click, right? Remember our definition of zero click, no special access, no proximity, no user action required to get infected. It's just the phone's in your pocket, it can get infected because it's automatically deserializing or processing something. So you don't need persistence in that case. You just persist by refiring the exploit again. And you could also potentially think about disabling certain updates or breaking certain security features on the phone to make it easy to reinfect and ensure that if your exploit is ever patched, you don't lose that persistent access to a device that's already been infected. Okay, so that was pretty interesting. One of the other interesting things we learned from this sample was a clever technique they were using to subvert iCloud two-factor authentication. So I'm sure everyone in this room has used 2FA, you know what it is. This is a 6-digit code or what have you that you type in when you have to sign into your Apple account. It's mandatory on Apple. Other services have it as optional. The way that it works at a very, very 100,000 foot level on iOS is that there's a process on the phone which is some black box, add ID, also called NSET. Its control flow is obfuscated with Apple's Fair Play DRM. It's quote-unquote hard, although not impossible, to reverse engineer. But why would you bother reverse engineering it when you can just treat it like a black box? So what they do is they actually inject some code into this add ID process, which allows them to, in some way, control the generation of these codes. So I'll explain how that works in a second, but I'm going to throw it over to Christine to explain a little bit about how this code injection works on iOS.
So a common technique that a lot of threat actors use is called dial-up injection, and this is how they can circumvent the inability to hash binaries and run a binary on disk. So what they do is they actually write to a dial-up, and then they have that dial-up loaded into memory, and then is executed by the target process. So by doing this, you're able to inherit all of the permissions, all of the entitlements that target process has. So there's some really awesome code that Jonathan Levin, who you might be familiar with, he wrote like all the iOS, macOS folks. He actually has some POC code on his website that I'm going to walk you through. So the first thing, and remember, it's really, really hard to get to this point on iOS because you need to have root access to be able to do this. So imagine that we're the threat actor, we have bypassed all of those mitigations. This is how they take that next step and control iCloud 2FA. So the first thing is they need to find the PID of the target process, which in this case is add ID. And so you need to grab the task port for that using this very useful function, task for PID. The next thing is you need to allocate memory within the process that you have the task port of, because you are about to write shellcode into that memory. So you allocate some memory, and then you're going to write some shellcode into that memory, then make it executable so that the shellcode will run. But you might be wondering, well, like what is supposed to be in my shellcode that is just like running in memory? And so the shellcode is actually going to leverage what's called the DYLD shared cache, which is like a shared library that's actually shared by all iOS system processes for various different functions, such as dlopen. So you are going to have some shellcode that has a pointer to dlopen, and you're going to dlopen a dilib on disk that has all of the malicious functionality that you're interested in executing. So this could be overwriting functions that you need, but it's all things that require the entitlements that add-ID already has. So the last thing that you do in order to kick off this shellcode executing is you have to spin off a thread. So by executing a thread out of add-ID, you are not spinning off a new process, so AMP will not bother you, but you are executing still within the context of add-ID, which grants you all of those entitlements that you need to do the things with iCloud 2FA that you need to do.
So what do you actually do with this injected code? Well, we recovered and analyzed the code that was injected into the add-ID process. And essentially, what the code was doing relies on understanding the scheme that Apple uses for these two-factor codes. It's pretty standard, TOTP, time-based one-time password. In other words, the sole inputs to the function that is generating the two-factor codes are, number one, some private key material, and number two, the system time. What does the parent block call time? So what this code does is pretty clever. It simply fools addID into thinking it's the wrong time. In other words, it hooks the get time of day function and allows the Spiral's operator to send a message to addID to change the clock, from addID's perspective to some arbitrary time, and then request the generation of a two-factor code valid at that time. So you can see where this is going. They set the clock to the future and generate two-factor codes that are valid for arbitrary future times, exfiltrate those, and great. They have some sort of persistent way, semi-persistent way, to get around iCloud 2FA without having to persistently change anything on the device. One of the other interesting features, besides the kind of unique functionality of what it could do that we haven't really seen before, is the ability for the spyware's operator to configure pretty complex rules that could govern the spyware's functionality based on inputs from sensors on the phone. So for example, they could condition certain actions, like only exfiltrate when the VPN is disconnected or when there's no proxy set. And cause the spyware to delete itself if a third-party jailbreak is detected, defined by some hard-coded paths. Is there a device attached via USB? Maybe that indicates the user is trying to debug their device or is trying to capture a copy of the spyware. In that case, you could hide the spyware, uninstall it, any number of actions. You might want to do certain things when the screen is locked or the screen is powered off, right? You probably all know that the phones these days have the little lights that come on. Oh, something's using the camera, oh, something's using the microphone. So if the screen is turned off, maybe that might not show. So you might want to do certain things when the screen is off. You also can condition things based on temperature of the battery, which we found really interesting. But it actually makes sense because a common complaint that people come to us at Citizen Lab with is, oh, Bill, I'm sure my phone is infected. It's running hot. That's a sure sign that my battery is draining. So this is a way that the operator could get around that, right? They could say, oh, well, if the battery is draining too much, stop draining the battery. If the battery's getting too hot, we'll stop capturing data for a while and wait till later. Also, of course, any sort of connectivity change, going to a new country, going within certain coordinates, you might want to trigger different behavior. And the operator can also and or not or pipe these together. One of the really curious things which led us to the theory of the exploit is we found that the spyware could receive a cleanup command from the command and control server that was managing the spyware infection. And upon receipt of this cleanup command, the spyware took 3 steps. The first step is it would open a file called calendar.sqlitedb on disk. Now, those of you who have an iPhone know that there's a very tightly integrated calendar app on the phone. And you know that you can have shared calendars with your friends, you can invite your friends to various events. When you invite your friend to an event, the friend will receive a pop-up notification from the calendar app. Christine has invited you to Disctrict Con or something like this. Do you want to accept? So this is what the calendar.sqlitedb file is driving. It's driving sort of the calendar app's local view of the state of a shared calendar in iCloud. So the cleanup command opens this file. It runs several queries. The queries are all delete queries. And they contain a parameter, an email address supplied by the command and control server. So essentially what this is doing is deleting various traces from various tables for anything pertaining to an event about where the inviter is a certain email address. And then after this is done, because SQLite databases sometimes might persist deleted data, they do a vacuum of the database to make sure that deleted data is not being left around. So this is pretty interesting. We're thinking, okay, well, spyware typically exfiltrates data. It doesn't often delete data, unless there's something it's trying to cover up. So we thought, maybe this is a clue about the vector.
So what ended up happening was we realized that there might be something in the initial forensic analysis of the device that was missed. So Citizen Lab went back to the device to see, are there any calendar invites on here that we don't see? But of course, they were deleted. However, even though the threat actor did this CNC cleanup command on the device, it did not go to where the backup of the calendar invite is, which is actually on the CalDAV server. So we're able to recover the original calendar invite from the CalDAV server to figure out, was this potentially the initial exploit vector used?
Yeah, so this is essentially what we recovered. And one sort of primer on the architecture of the protocol for synchronizing the calendar between the phone and the server. So it's at the top of the protocol layer is this thing called iCalendar. And iCalendar there's an RFC for it. I think the development of the standard was mainly driven by folks at Apple, hence the name iCalendar. But iCalendar is essentially like a pretty easy to read plain text format where it's sort of key value delimited. There's certain keys that have certain values which tell you things about the event. So there's some defined keys like, I don't know, like DT end or something which tells you the time zone and date and time at the end of the event, and organizer, UID, DT stamp, location, things like this that encode various information about the event. And of course, the creator of the event can, as they see fit, define arbitrary keys and values. Now, the interesting thing about this iCalendar protocol, it's completely plain text, no structure, nothing in there beyond the key value pairs. This is transmitted between the server and the phone over the XML-based CalDAV protocol, which is in turn based on top of WebDAV and XML and all pretty complex stack. So one of the things that we noticed about this event and why it stood out to us, like how do we know this is suspicious? The first thing is the event was added 6 months after the end date of the event, right? But this is a bit odd, unless you're like, Stephen Hawking inviting, time travelers to an event in the past. Like, this doesn't really seem plausible, inviting someone to an event in the past. The other thing which we realized, which Apple has since fixed, is that before Apple fixed this, if you sent an invite to someone for a past date, there'd be no notification generated on the device. So invites to future events, notification, blah, 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 has invited you to an event. Here's the name, here's the details, do you want to accept or not? But for past events, notification not generated. So that was interesting. Furthermore, we noticed something very odd down here, which is that, so iCalendar defines keys called description and attendee. But in this case, the description and attendee tags in the key have these weird, like, closing and opening CData tags, which are absolutely, definitively not part of iCalendar at all. There is no XML in iCalendar. This was very, very strange. And as I sort of alluded to earlier, what's going on the wire here between the phone and the server is this iCalendar plain text blob is being thrown into the middle of a XML blob, which is the CalDAV WebDAV thing, and the calendar event is included within this this opening and closing CData tags. So essentially, what the attackers what it looks like they're doing is closing off the initial CData tag, potentially inserting XML, although we didn't see any XML in the calendar event we recovered, but I'll get to that in a little bit, and then reopening the CData and including the rest of the event. It's kind of interesting, right? It's a way to get access to the code path on the phone that's parsing the CalDAV XML document in a way that you're not supposed to have access to. So wait a minute, does this really work? Well, yes, we tested it. So if you send an event of this format to the phone, the thing in between the closing and the opening CData tag hits the XML parser. It's libxml2 in SAX mode. There's not vulnerabilities every day in libxml2, but you could imagine potentially something going on there, or Apple's wrapper around libxml2. Though we don't know specifically what was exploited because the XML was not included in that event that we recovered. And we'll get to that in a little bit. And this is totally cool with the phone's iCalendar parser because the iCalendar parser disregards anything that's not in the CData tag. So it doesn't even close its eyes when the XML is being parsed by libxml2, and then opens its eyes again when the CDA starts. So what we're only see is a perfectly valid iCalendar event on the phone. So there's no crash or no warning generated within iCalendar with the calendar app. And this is all well and good, right? But can we actually test against the server, right? So we're uncovering this attack. We're looking into this case after it was conducted and after perhaps there have been some fixes implemented. But fortunately, yes, Apple does release, or did release, the old version of their iCalendar server. They have a newer version, which I guess is not open source. But they open source the old version. It's on GitHub. You can download it and pop it open in Ubuntu VM and test it. So we're able to verify a couple things. First, we verified that the server, in fact, does reject the closing and opening CDA tags, but only if they're in the value portion of the key value pair. If they're in the key portion, it will happily accept them and store the event on the server and return that to the client when it's requested. Additionally, and this is where we got thwarted by Quadri's cleverness here. It turns out it is possible to update an invitation, though it's not possible to completely remove it from someone's calendar, and it's not possible to delete a key value pair, but you can update the value of a key value pair. So what we think the attackers did in this case is they updated the value of the description, close square bracket, close angle bracket key to remove the XML exploit they were using and just included the letter X. And this is borne out by the fact that the event that we recovered had an update counter of 1, which is 1 more than 0, which is the initial value for the update counter. So the event had been updated once since the initial version. So we think that there was this update by the attackers that removed the juicy XML stuff that would have allowed us to exactly zero in on what the precise issue was that they were exploiting. Nevertheless, this was a interesting case in that it's one of the few known, perhaps the only known case of an attacker, a zero-click attacker on iPhone, totally eschewing iMessage and finding a different zero-click service.
And much like Drake's career, Quadrim is also defunct, so it's ironic that we chose City. So after our reporting on these exploits, both Microsoft and Citizen Lab reports, Quadrim actually declared bankruptcy and shut down for good. So we had some really cool impact from doing this work. Alright, so just some quick takeaways. First thing is collaboration and information sharing is so important. We wouldn't have even thought to find that calendar invite and query that CalDAV server if we had not been collaborating. We wouldn't have been able to because we didn't know any victims, and Citizen Lab would not have had the information about the calendar being vacuumed. So really awesome benefits of collaboration. Remember also that cloud services are a new vector, and as convenient as it is for me to be able to send you a calendar invite just by knowing your Apple ID, that convenience factor is what's introducing this cloud-based threat vector, because now these PSOAs are able to target based on Apple ID, because they can conveniently deliver an exploit to anybody's iMessage or iCalendar just by knowing their Apple ID. So when creating these new features, just remember that cloud vectors are not only convenient, but an actual attack surface that should be managed appropriately. We also want to build the ball broader, not just taller in one place. So Apple's done an amazing job with Glassdoor, and they're actually expanding it to other services, which is awesome. And so other platforms should take this into consideration as well, because you want to make sure that you have full coverage of all different services, not just one or two. And lastly, lockdown mode is a really amazing feature on iOS. However, it's optional. It's not on by default. So you will not be protected by all of the features of lockdown mode if it's not on.
Yeah, to echo what Christine said there about lockdown mode, we think that lockdown mode would have blocked this attack had lockdown mode been available at the time. It wasn't introduced to iOS 16, this attack was on iOS 14. But one of the important general philosophies behind lockdown mode is the idea that there should be no complex interaction possible from an untrusted iCloud account to a device that is lockdown mode on. So a bunch of automatic parsing is just turned off if the user that you're receiving the complex data from is not in your contact list. So lockdown mode is a great feature for sort of individualized defense, but whether lockdown mode alone moves the needle on the broader systemic issue remains to be seen. However, Apple is fortunately, as some of you may have seen, sending out notifications to individuals that they identify who have been hacked or targeted with certain types of spyware. Meta recently sent out notifications as well for Paragon cases. So it's good to see that positive development. So we do want to make sure to commend industry and cloud platforms for going in that direction. We'd like to see, I think, more of that as well, both because it has the potential to have systemic impact, as well it can help direct attention to and uncover cases of abuse. So thank you.
Thank you so much, everyone.
Thank you guys so much. A couple of security things. Make sure that your badge is on and lit so we can see it. Also, you guys don't know this, but there's a badge challenge on your NFC tag for your badge. Top 2 scorers by the end of tomorrow get a free ticket to next year. So.
Potentially with power next year. A few other announcements. As Winona said, please wear your badges and turn them on. Those who have booked at the hotel may be hearing from the hotel. Please use their rebooking link to a hotel that has power. If you're already checked in, I think you are fine, but if you work with the hotel directly. Those who need food should look south of L Street because that's where the power is still on. There's a good food court called Western Market that is open and expecting people as needed. Thank you for bearing with us as we do our best to have power. Policy Roundtable 1 is now going. Please go across the hall for that. Coffee, are people finally going to listen? Coffee is served. Go out the doors and to the right to the chill out area where there is artisanal coffee. And in 2 minutes, the next talk will speak, so please move out or be seated to be excited about Chris Bellows speaking about breaking a boot bomb on a trip we'll tell you more about.
Yeah, we're good. That's fine. Roro, can you turn it toward him? Yep.
Hello.
Hi.
We need to split this. Split this. It should be something here. I just moved this projector through this. Because
Yeah, it's fine.
Okay, can you put it right here? This projector? Yeah. This is ridiculous. We have power cord for this, right? Yep. This one's plugged in right here. What are you doing? That's one power. Oh, but it didn't spin already.
All right, thank you everyone. To continue on topic, please welcome Chris Bellows, who's going to be speaking about breaking the DA 1469X boot rock. And please bear with us and Chris as projectors deal with power surges for people who take the elevators. For those who would like to follow along on your phone, his PDFs are now on the online schedule link from the website, so you can respectfully stare at your phone while he talks.
Are you streaming still?
We're streaming.
Okay.
Yeah, so we can hear.
Where is the little clamshell with the?
It's up there. It's behind the confidence monitor.
Okay.
You okay leaving it there?
Yeah, just when you've done. Yep.
I have green light.
Yeah, I just did that. I feel like this is a fire situation about to happen.
Oh, the whole hotel is right now. Yeah, isn't that great?
The extinguisher.
Did it crap out?
Yep. Looks like it just did.
Which one did you? Where did you plug it in?
I haven't streamed the power strip.
Oh, this went right down to 0%.
This guy's dead. We're not using it.
You all can't see this, but if you're following along, I'm Chris.
Where is this?
Research Science Director at Trace Partners, also a professional owl illustrator. If you're looking at the slides right now, I'm calling out the owl illustrator, and I did not realize that this is something not a lot of people are aware of. There's that kind of classic, funny picture of how to draw an owl, and it says draw 2 circles, then draw the rest of the owl. I think in embedded work or reversing in general, we encounter a lot of owl problems, and I like to reverse these owl problems. So if I call out drawing an owl, or there's the owl, that's what I'm talking about. So kind of the driver behind this research is at Atreus, we don't have a sales team. People who scope the work are the people who do the work. In this case, we had scoped some work on this embedded target we had not encountered yet. I had a little bit of research time before that actually occurred. So I decided to buy a dev kit, dig into it, and try to give the testing team a head start as far as what this device is and provide them some documentation.
What about the little one I had?
So the device is kind of mentioned in the name as the DA1469X from Renesas. According to their marketing materials, it is a microcontroller targeting small, low-power Bluetooth, low-energy systems like fitness trackers, watches, toys, home automation, and stuff like that. But at the end of the day, the things we really care about are the security things, like secure access, how is the debugging interface is turned off, secure boot, which is going to validate that application as it's started. This one in particular, it provides this encrypted firmware, and that allows the developer to load an encrypted application from external flash onto the device. So on these devices, I'm kind of high level just covering this. Some people may be familiar, some not. So all these security controls are handled by the system's OTP or one-time programmable segment. It's a write-once area that allows the developer to kind of write those values in and control whether those are on or off. And once they're set, they are set. Ideally you want to turn off. Sorry, bear with me here.
You have part of mine. Oh, I'm sorry. Okay.
It's just not gonna explain.
Sorry. So the developer can write to that area, configure those things, do things like turn off JTAG, single wire debug, or some sort of a lot of times there's like a serial bootloader that allows you to reload if you need to. In this case, there's also the idea of these encryption keys. Those also get written to this one-time programmable area. There's actually room for 8 keys for the
QSpy Flash, some user keys and then public keys that are used to do the validation. When those are loaded in, they are accessible by the crypto controller and referenced by an index into that.
How do you get it to?
So,
Plug it into the.
again, you mentioned the idea of this encrypted applications. In most embedded systems,
Oh, no.
on the controller, the application gets loaded onto embedded flash, which at the end of the day, it's going to be protected by disabling the debug interface, so like readback protection and stuff like that. In this case, the application is loaded from that external spy flash, and to defend against attackers who can physically access that, since it's not protected by the debug interface, readback protection, they chose to deploy encryption.
You just hear it.
In this case, it's operating in AES CTR mode, and the reason that is that allows them to decrypt arbitrary blocks on the fly, and instead of having to decrypt that whole application at runtime. And again, we touched on it before, the kind of the most important part in defending an embedded system is secure boot. Secure boot, allows them to sign that application, and when it's started, that is checked against those public key values that are stored in the runtime programmable areas. And on this particular device, when secure boot is enabled, it cannot be disabled. And once it has been turned on, all those previous items are also enforced. So you have to be using encrypted applications, etc. So with all those things, how does someone audit? Do these things work? And that's going to be the job of BootROM. And that is a small block of code that's written in the device, and it's executed every time the device is powered on. It initializes the base state of the hardware, and handles that transition to the user's application. Since the code that's physically part of the hardware, it's immutable and it cannot be modified after that part leaves the factory. Immutable code kind of offers a strong defense against attacks, since it can't be modified without access to specialized equipment, like focus ion beam or something like that. The downside is that any bugs that are identified can't be fixed, and it's going to require a brand new fabrication run. With the exception, if that vendor has some sort of small one-time programmable area that will allow them to patch and kind of, jump to other areas, a lot of times those are undocumented. I think the notable examples for the BootROM bug that most people are familiar with would be the iPhone, like Fine Ring, Checkmate. So getting to BootROM, sometimes it's accessible. You can just pull it out, it's not a big deal. Other times it is locked down, and actually, so to get a hold of it, you need bugs. In the case of this particular chip, the BootROM's mapped range that's in the document, the data sheet. And the easiest way to get a hold of that is connect a debugger to it, like JLink or OpenOCD or something like that, and just read the contents out of the disk. And once you have that, you can actually, start that drawing the owl process, loading it into a decompiler or whatever your tool you like, and kind of figure out, okay, what is this doing? So there's a lot of challenges when dealing with something like a BootROM. 1 second, let's see if this works.
Yay.
We're back. If I can figure out how to do that. Are we good? All right,
Yeah.
perfect. That makes this much easier. So as the BootROM, that's hard-coded into the chip. There's not a whole lot of space on the chip to do that, so the code has to be dense. And that means, there's not room for common external libraries, debug statements, friendly strings, etc. And it can be scary or a terrible feeling when you load something up into IDA or whatever tool you're using and you see no strings. Because a lot of times these are easy kind of cheats to figure out what's going on. So how to work around that. So while all those like debug strings and helpful details aren't there, to use as a starting point, kind of the fact that the job of the boot ROM is to initialize that hardware and pivot to the user application kind of makes things easier. By going with the data sheet, you can identify all those memory segments and registers and peripherals, and use that in your tool as a guide to identify functions that are referencing those. So, segment creation and all that stuff will be done manually or using scripting. Really the easiest way, if possible, is use an SVD file, which IDA actually has a loader built right in, which that wasn't always there. It works fairly well. The SVDs can be found online, often like SDKs or IDE or some debugging tool will also ship with those, since they use them to kind of fill out those in the user interface as far as what registers there are and how they're configured. So once you have your segments loaded, that documentation into your tool, in this case we're using IDA, it's a lot easier to kind of work backwards from the hardware registers to functions that are accessing them. And the kind of example that's shown here is the UART line controller, which is used to configure the enables boot. So kind of as noted before, that the product header sections are completely open for modification. Talking through that, it seems, okay, that's great, it works. But see, the calculated matches the stored one. The size of the header is calculated using a value stored in that header. And most importantly, it's used to copy into a fixed length buffer some value. And that, calls out here, ends up in an overflow of the stack. And the last one here on the bottom was kind of a distraction. You can loop that around to 0, but there actually was not a path to actually use that. It tried really hard to get an exploitable path in the payload, you have to fail the first CRC check with an invalid CRC in the primary. Next, the payload contains a backup header with a size larger than the target buffer that has a valid CRC for its size. The backup product header ends up clobbering the first target buffer, and you win. And everything's great, except it does not work like that. In order to pivot into the controlled stack, you need to successfully exit the function and go back to the boot flow. In the current state, it's just an infinite loop over and over again. The function will be exited by placing a valid CRC that is pre-computed for that new large primary header that's created at the correct offset from the primary. And then when it loops back, that primary passes, it will exit the function into the controlled stack. The other option is you can literally ground out the SPI flash and cause that to fail, and it will exit the function. And that was honestly the first thing I tried, since it was kind of painful to figure out how to get out programmatically. So this single payload kind of meets all those requirements to gain code execution. It contains a primary header with an invalid CRC, an oversized backup header with a valid CRC, and a pre-computed CRC with a new updated primary header. By flagging that on there, on a device that has secure boot, but debugging still enabled, you can kind of walk through and see that, setting a breakpoint at that vulnerable call, you can see that at the point it's called, R1 holds hex with 3149, and that destination buffer is at R0. And then you have that before and after memory snapshot here, and that shows that original save return address get overwritten from the value in the previous. Halting right before that function exits shows that the execution's passed to our control address, ending up in that infinite loop from that image. And kind of backing up to see, okay, where is this in the boot flow? This is before any secure boot functions occur. So it kind of invalidates that whole thing. Renesys did confirm and acknowledge that, and also this requires a brand new production run to fix, so this isn't forever bug. Again, it's shown in that previous mode that unprotected configuration values are difficult to handle safely. The firmware security header provides writable values to configure boot ROM for invalidating the signature as well as decryption of the application. The boot ROM configures the hardware encryption engine with the values specified in here, setting the index to the correct key, writing the nonce value that is used for encryption of the application. The nonce actually ends up being the IV into that function. And again, we kind of called out that CTR mode is used because it allows decryption of arbitrary blocks, which facilitates execute in place. The downside is that none of this is authenticated, meaning the only way it can detect that something bad went wrong is crashing. This here is like, I looked at this and this was the question I asked someone at work, because this did not seem plausible. Maybe you could get lucky and execute some uncontrollable code, but not an arbitrary data, no matter how many salt lamps or crystals I had on my desk. So thinking of the idea a bit more, I started looking at potential paths. The first blocks of the encrypted application are the ones that are going to matter, since they contain the initial address of the stack and the reset vector, which is the first function that gets called. The documentation shows that the QSPI flash memory space is pretty large and is mapped at 2 locations, which gave me some hope, but we had the question of could a modified nonce result in setting a reset vector to an address in that range? So instead of doing this on device slowly, it was just faster to simulate this process by creating a quick script that decrypts a block of an image using a no-nonce key and seeing what fell out. I didn't expect much, but it didn't take long to get lots of hits that matched this, so that was promising. The last step is does this actually work on the device? So, using a device that is configured with debug access, going through and setting it up and setting a breakpoint where that reset vector gets set, and determine does it match that value? Will this work? Can we jump to this place? This kind of shows that. That last bit on the bottom is just calling out. I wasted a lot of time here. If you're in the JLink and the T-bit does not match the address we're trying to jump to, it's super helpful, and it will just go ahead and fix that for you and allow it to go. So chasing my tail on why does this work when I'm debugging it, but not work when I actually try to do it outside of the debugger. Hopefully you all won't run into that. So this looked feasible. One important part to cover is where does this occur in the boot diagram? And since it's after that validation, you need to ensure that validation passes, which ends up being fine since we're operating outside of that protected area. So anything after the application is fair game to place a payload. So with a known encryption configuration, it's easy to do this, but on a device, is this possible? And how do you detect if it's possible? And really the initial kind of idea here is you just fill it with nonce and monitor QSPI, and you can see if what you did worked or not. But again, nothing is easy. QSPI is a lot harder to monitor than I thought. My logic analyzer wasn't able to do that. The plugins I tried weren't successful. The other issue is these tend to use very, very tiny flash chips, and that means there's no place to expose a pin or a pad and tap into that and monitor it. So you end up having to take it off and make crazy hacky things like this. So instead of trying to monitor it in full, what about just one wire? And it's where I identified just monitoring the serial in. You can see there's a huge difference in a modified nonce that fails at boot loops versus the original. So that gives a good tell. The next step would be automating all this, and I let this run overnight. I got 241 captures, and it was actually the 154th. Looked nothing like the others. And going ahead and replaying that again, you can see that, yeah, that actually worked. It wasn't just a bug. So by confirming that, you have to figure out where it is, and it's kind of just chopping that smaller and smaller and smaller until it stops working, then coming back and adding until it works again. That'll tell you where that actually occurred. The other little trick I discovered is going back to the documentation. You can control what spy flash command is used And here, this ends up being, you can just set it to single-file mode and monitor it easily. And so here you can see, use my monitor, that's the exact address I calculated, so now you have that tell. The third trick here is there's this idea of auto mode, and you're not allowed to write to the SPY flash while it's in auto mode, which auto mode is required to do that on the file encryption. And I'm being told that I'm out of time here. So, at the end of the day, it comes down to writing this payload that reads that out and switches between auto and manual mode. It writes the decrypted value out using an invalid SPY flash, and you can go through and scrape those logs out and actually get that encrypted data. Again, when it says confirm this, it doesn't give you the key, but it, the things it's protecting are exposed. Again, this requires a new fabrication run. Real things that use this, Princess Cruise Lines use this for their access on their ships. Of course, people sell them on eBay. I have no idea why. So I bought some, and I took it apart, and they're not encrypted.